Professor William Chueh is an associate professor in the Department of Material Science and Engineering and senior fellow of the Precourt Institute for Energy at Stanford University. And then Professor Chueh has received numerous honors, including the MRS Outstanding Young Investigator Award in 2018, Sloan Research Fellowship in 2016, NSF Career Award in 2015. Also in 2012, he was named as one of the top 35 innovators under the age of 35 by MIT Technology Review. So he's going to talk about the emergent electrochemical phenomenon at the nanoscale. So please welcome him with a big hand.
Thank you very much for the kind introduction. Can you hear me okay?
Yes, we are. Yeah.
Perfect. Thank you so much. And let me add my thanks to Edu for his organizing this excellent symposium. And it's a great pleasure to speak right after Bo-Hyung, who is an outstanding alum of our department at Stanford. So today I'd like to spend some time talking about emergent phenomena for electrochemical systems at the mesoscale. I think we heard a lot of talk about nanoscale, and mesoscale is something that is less explored. And I want to provide some context before I dive into some of the new understandings. What I'm going to talk about today is electrochemical ion insertion. And this is something that has been known for more than half a century. For example, you can put protons into tungsten trioxide. You can put lithium into olivines and layer oxides. You can put oxygen into perovskites. You can put lithium, potassium, and sodium to graphite. And you can put all sort of things into transition metal dichalcogenides. But really, the field of electrochemical ion insertion has flourished because of the many application areas. So there are two groups of applications. On the left, we have dynamic switching. So this is where inserting ions into these inorganic materials will change its properties. And on the right is chemical transformation, whereby the ion insertion results in a change in the material property that can be used and harnessed for chemistry. So perhaps the most well-known application of ion insertion today is lithium-ion batteries. And here you have your standard two electrodes, an electrolyte, and you're shuttling lithium in between. Another very well-known application for ion insertion is electrochromics. So this is behind the electrochromic windows used on the Boeing 787 and smart buildings. And the concept is not very dissimilar from a battery, but rather than using it for energy storage, you use it for changing optical properties. And there are many other emerging areas of applications. For example, ion insertion is used to improve electrocatalysis. It's also used for desalinations and separation. On the switching side, there are also interesting and exciting efforts using ion insertion materials as memory devices, for example, as memristors. And then yet another emerging application is using ion insertion to tune thermal conductivity in order to make thermal transistors. And the topic of ion insertion is really a rich science and engineering area that spans many time and length scale. And this is a plot I like to use to describe the many time scales and length scales involved. So on the y-axis, we have length time scale all the way from picoseconds to years. So picosecond, it is the time scale of ionic hopping at a single lattice site, and years is the lifetime of a device based on ion insertion. On the x-axis, we have length scales. Again, we have angstroms for ionic hopping, all the way to meters for devices. And as we go from short time scale and short length scale, we have many approaches. We have material chemistry. At the larger length scales, we have nanomaterials design. At the higher length scales, we have device fabrication. And you can take it all the way not only to devices, but also to systems. And there are many approaches for understanding each one of these length scales. And all the electrochemical ion insertion technologies I mentioned on the previous slide requires integration across all of these scales. And here at Stanford University, we have chosen to focus on one particular application, which is energy storage. And Chueh, my colleague, who is the co-director, along with myself, of the Storage X initiative at Stanford, aims to assemble a large team of people, about 150 at Stanford, to tackle energy storage in terms of electrochemical ion insertion, from materials to devices to systems. And here are some of the colleagues that we work with to achieve a length and time spanning understanding and control for energy storage. So now I'd like to give two examples of what I mean by length spanning. So take the familiar concept of phase separation. This is something students learn in material science classes. No doubt many of you, many of the students at KAIST have seen this multiple times. So let me just give an example of phase separation. In the case of ion insertion, you can have phase separation at the atomic scale. So for example, here we have a layer material like graphite, and you can have staging of ions inside, changing the periodicity at the atomic scale. You can then move up one length scale to a few nanometers, and this is a situation of surface phase separation, where, say, the surface of a particle could have a different phase than the bulk, driven by interfacial free energy. Then you can go to the scale of single particles, which could be from tens of nanometers to microns. And here you could have phase separation, and you have, say, compositionally rich and compositionally poor phases driven by the double whale free energy. And you can even go to ensembles where you have many particles. So this is certainly the case in a porous electrode for a battery or electrocatalyst, where you have many, many particles connected ionically and electronically. And you can also have phase separation not only within particles, but also between particles. So these are the many length scales that one aims to understand and control when it comes to battery technologies and other ion insertion technologies. Another example is ionic transport. This is another very exciting aspect of ion insertion that also spans a wide range of scales. So for those of you studying electronic materials or optical material that Byohan alluded to earlier, we're talking about electronic phenomena which happens at the femtosecond scale. But ionic transport actually happens at quite a bit of lower time scale, starting at the picosecond for atomic hopping, all the way to microseconds for long-range transport. And this is due to the fact that we have energetic barriers on the orders of 100 or a few hundred millielectron volts and a hopping distance of 1 to a few angstroms. So ionic transport, just like phase separation, also span a wide range of scale, in this case, time and length as well. So the application I'm going to talk about today is batteries, specifically lithium-ion battery. And one of the themes that we try to highlight here is embracing dynamics and heterogeneities in lithium-ion batteries. So take all the concept I just described earlier in terms of phase separation and ionic transport, and now let's look at it from the lens of a device. So you take a cylindrical lithium-ion battery, you zoom in, you can see the jelly roll inside. If you zoom in further, you can see the porous electrodes, the positive, the negative, and the separator. You zoom in more, you can see the building blocks of the agglomerate particles, which then consists of primary particles of a few hundred nanometers in size. And if you zoom in further, you have the lattice of the crystals that make up the electrodes. And then from going at the cell level to the particle level, you span energy scales from watt hours to picowatt hours. So this is a tremendous range of energy scale that makes it very difficult to fully understand. Let me give you a few examples from Stanford that looks at the heterogeneities and dynamics at all length scale. So this is a study of just taking a battery apart in the charged state. So the color you see here is due to the color of graphite. So when graphite has lithium inside, it's gold in color. And when it doesn't have lithium, then it's black. You can see the top is a pristine battery that's lithiated uniformly. On the bottom, you have a degraded battery where it doesn't lithiate near the edges. And this is done just with an optical inspection of the electric sheet. The scale bar is 10 centimeter. If we zoom in a little bit further and we look at the tens of micron length scale, we can look at an conglomerate. This is a battery positive electrolyte cathode particle. And here I'm showing the microstructure as elucidated by synchrotron tomography. And the color you're seeing here is actually the local oxidation state at the mesoscale. So here you're looking at the particle, which have extremely heterogeneous distributions of oxidation state. So this is something that is also prevalent in batteries, is you have heterogeneities that spans all the way from the devices down to the particles. If we take just one of those particles and zoom in, so this is now a primary single crystalline particle. Again, the color here corresponds to the oxidation state. And you can see as the battery undergoes cycling, charging and discharging, you also have a very non-uniform change in the oxidation throughout the material. And it doesn't stop here. If you now go to the atomic scale, we can use cryogenic electron microscopy, for example, to look at the interface between the liquid electrolyte and the negative electrode. In this case, this is the so-called SEI that is between the electrolyte and carbon. And you can see this is on the order of a few nanometers. And this is also something that changes as the battery cycles, going from something that's quite thin and compact to something that's quite extended and amorphous. And this contributes to the degradation of the battery. And we can go to the atomic scale. So if you take, say, a battery positive electrode like lithium cobalt oxide or its related compositions, you can see that initially the material is very pristine. You have very good order in the material. All the atoms are in their supposed locations. But just after you remove lithium and insert lithium back into the structure, then the structure disorders at the atomic scale. So this very quick journey I took you through, coming from the devices all the way down to the atomic level, really showcases the wide range of heterogeneity and dynamics in the battery, ranging from the macro scale and the device scale all the way to atomic, and ranging from the lifetime of the battery to ionic hopping. So we know a lot about batteries and other electrochemical devices, but a lot of times these heterogeneities we see, we simply chuck it up to unexplained heterogeneities. What I mean to say is you read in papers quite a bit, say, well, it looks heterogeneous. And what I want to do today is to provide some insight in terms of a physical understanding at the mesoscale. We want to go beyond these so-called unexplained heterogeneities and then try to put together a framework for understanding these heterogeneous phenomena at the mesoscale, and then from these understanding, derive a set of design rules that can help us engineer better batteries and other ion insertion devices. So I will talk about three main themes here, these emergent phenomena. The first theme is population dynamics. So population dynamics refers to the fact that an electrochemical system is not just a single crystal, it's actually consisting of many such single crystal. In a typical cylindrical battery, you have several trillion individual particles that may span the nano and the micro scale. So how this system behaves as an ensemble of particle is actually something that's quite interesting and not very well understood. So this is the first theme. The second theme is another interesting phenomena called autocatalysis. So for those of you who have chemical engineering background, you will be familiar with this word. Autocatalysis means a catalytic event that speeds up as it proceeds. And it turns out for electrochemical ion insertion, it has an autocatalytic property. So because you're changing composition of the material, you are inserting or removing lithium or other ions, as you insert them and remove them, the kinetics actually change dramatically. So this is just a schematic showing, for example, the diffusion coefficient of lithium can change widely as a function of composition, several orders of magnitude. And this autocatalytic behavior also can explain and account for some of these unexplained heterogeneities. The third and the final theme will be non-equilibrium thermodynamics. So many of the materials we use for batteries and other electrochemical technologies will establish phase diagrams. We know where the single phase regimes are, we know where the two phase regimes are. But the problem is that a battery operates very far from equilibrium. We're constantly applying current. We have an overpotential, which takes it away from equilibrium condition. So in order to understand the phase behavior of this material, we must understand the thermodynamic properties at non-equilibrium condition. In other words, what determines the stability of the system when the material is undergoing current flow and other electrochemical cycling. I'm going to divide the talk into two specific case studies. The first half of the talk will focus on a very well-studied system, lithium iron phosphate, which is the olivine crystal structure. It has one-dimensional channels for conducting lithium, and it's one of the commonly used lithium-ion battery electrodes. You can find them in electric buses and other high-power applications. This material is characterized by a very large miscibility gap. So I show here a schematic free energy diagram, so it has a usual double well. So this means that for a majority of the composition of the material, it will have a phase separation. So in other words, you will find this material either lithium poor, so close to lithium 0, or lithium rich or lithium 1 iron phosphate. So this will be the first part of the talk. The second part of the talk, I will take the opposite phase behavior, which is for a layer oxide. So this is lithium cobalt oxide or lithium nickel manganese cobalt oxide and so forth. And this is a two-dimensional material with van der Waals gap for conducting lithium. And this is another commonly used lithium-ion battery electrode, typically used for high energy applications for electric vehicles and consumer electronics. In contrast to lithium iron phosphate, the layer oxides have mostly a single phase behavior in the regimes of interest, which means it doesn't have a double well inside for the free energy diagram as a single well. So on the left, we have a system that naturally phase separates into lithium rich and lithium poor phases. On the right, we have a system that does not naturally phase separate. So I'm going to take the next half an hour or so to go through some details about these three phenomena for these two material classes: population dynamics, autocatalysis, and non-equilibrium thermodynamics. And again, the goal here is to start to explain some of these heterogeneities that we couldn't quite understand before. So let me get started on lithium iron phosphate. So as I mentioned earlier, this system has a very large miscibility gap. So you're going to find it either in the lithium rich state or the lithium poor state. And those are represented by the color red and the color green in this series of operando X-ray images. So we're taking a picture, a movie, of how lithium is being how lithium is being inserted into lithium iron phosphate as you discharge the battery. And this is done in situ. And if you start from the first frame here, you see that the electrode mostly is in a lithium poor configuration, so it hardly has any lithium. And then you start putting lithium in by driving a current, but rather than receiving the lithium uniformly, you can see these hotspots that I circled out. This is actually where the lithium is actively inserting. If you go through these series of images very carefully, you will find that only a few % of the particles is actively receiving lithium at any given time. So the system is very far from being uniform. If I show you a higher resolution image here, you can see that almost all the particles are either full of lithium, which is in red, or devoid of lithium in green, and only very few particles are actually actively undergoing intercalation, so it has a moving front of receiving lithium. So this is something that's very strange. We term this the active population effect, which means that only a very small fraction of the battery electrode is active for receiving lithium at any given time. So let me first show you a cartoon of what is happening. So when you cycle lithium iron phosphate very slowly, say over tens of hours, you see this mosaic effect whereby very few % of the particle receive lithium. So this is very unexpected because thermodynamics tell you that when you approach a system very slowly, it should be very uniform, but it is not the case. On the other hand, when we go to very high rate, so this is now driving the system very quickly, maybe in half an hour or 15 minutes, then you actually see a much more uniform intercalation, which means that the active population actually increases with rate. So here we have a very uncomfortable observation where the system is extremely heterogeneous when it's close to equilibrium, and the system is very homogeneous when it's far from equilibrium. So let me plot this for you. This is the active particle fraction. So this is the percentage of the battery electrode that is participating in intercalation. And then the bottom is C rate. So higher the C rate, the faster the reaction is. So you can see here at very low C rate, almost none of the battery electrode is active, as I showed in the movie before. But as you increase C rate, more and more of the electrode becomes active. So schematically, we have this mosaic effect where very small fraction of the particles intercalate at low rate. But at high rate, you have all of the particles participating. Again, this is very contrary to our standard textbook teaching of kinetics, where the system uniformity actually increases with rate. Let me show you another representation of this. This is the plot of the single particle lithiation time versus the electrode lithiation time. So naively, you would expect that the two time scales should match. And when the two time scales match, that means the entirety of your electrode is active. And when you charge and discharge lithium iron phosphate very quickly, on the left of the plot, that's what you see. 1 hour lithiation time for a particle corresponds to 1 hour lithiation time for the electrode, so you have complete utilization. But as you slow down, as you go to the right of the plot, you actually plateau. And the plateau region is very interesting because that means you are slowing down the electrode intercalation, but you're not slowing down the particle intercalation. And this is the regime where the active population drops and you're using less and less of the particle. So this phenomenon, which we discovered in the early 2010s, was very uncomfortable because this went against most kinetic understandings of intercalation. So we dug a little bit deeper, and let me show you just a cartoon of what we found. Essentially, we are looking at the population effect, which means that if you take a standard single particle kinetics picture, it doesn't apply. You have to think of it as an ensemble of particle, which is the reality in most electrochemical systems. So let me show you what happens. For a single particle, if you just have one single crystal of lithium iron phosphate, this blue curve is your chemical potential. So this is basically the voltage of the particle as a function of the amount of lithium. So as you insert lithium, you are traversing this blue line. So this blue line is your open circuit voltage. So in order to pump lithium into the system, you have to apply an overpotential that is slightly higher than the blue. You will notice that there's a hump and a drop. That is the nucleation barrier. But because there's only one particle in the system, we only have to have nucleation happen once. So once we nucleate the new phase, so remember lithium iron phosphate has a very large miscibility gap, then the phase transition commences and the intercalation can continue. So essentially, this red dashed line represents the actual chemical potential, and the difference between the red line and the blue line is the driving force. So you basically trace over the blue line. So initially, you are inserting lithium, and as you ramp up your current, you're increasing your driving force. So you need to raise the red line a bit, but you will still follow the shape of the particle. So the current will get higher and higher and higher for your single particle. So here the width of the arrow represents the magnitude of the current. But what happens when you have many particles? Well, in the single particle case, you only need one nucleation event. However, in the many particle case, you need to have one nucleation event per particle. So if you have many particles, you need to have a constant rate of nucleation in order to maintain the current that you're asking the battery to accept or deliver. So now the situation is very different. You need to have particles overcoming this nucleation barrier at a finite rate. Okay, for example, a certain number of nucleation per minute. And because of this requirement, this nucleation barrier pins the chemical potential or the voltage you are applying. So you have to constantly be at a potential that is greater than your nucleation barrier in order to keep the nucleation events coming. And then because of this pinning, that means the driving force, or the difference between the dashed red line and the blue line, is almost constant. Let me show you schematically what happens. So when the rate is very slow, when you're cycling the battery and intercalating very slowly, your red line is just slightly above the nucleation barrier. But now if you want more current to come out of the battery, you would just slightly increase the position of the red line to increase the driving force, but nucleation rate is very sensitive to potential. So then you will cause more particles to nucleate at a faster rate, but each one of those particles approximately sees the same driving force. So that's why the arrow, or the speed of intercalation per particle, remains the same. So as you increase the current, you are tuning up the intercalation and the nucleation rate, but you're not tuning the growth rate. And this is what fixes the particle lithiation time, because you're fixing the driving force for the growth of the second phase. What you're tuning here, it is the nucleation rate. And this is where the active population concept comes in. And it's not until when all the particle becomes active, then you start raising the red line considerably higher, because now in order to deliver a higher current, you now need to increase your driving force beyond the nucleation. Basically, this is when all of the particles have exhausted the nucleation event. So this is a brief insight into the active population effect in lithium iron phosphate. Now, let me zoom in now to one particle. So as I mentioned, lithium iron phosphate has a very large miscibility gap. So if you take a composition that is right in the middle of the gap, say lithium 0.5 iron phosphate, so half filled, and you let phase separation happen, then you can observe the phase separation using microscopy. So this is work done using X-ray microscopy, showing, again, lithium-rich and lithium-poor phases, where red is lithium-rich and green is lithium-poor. And lithium iron phosphate has a one-dimensional transport path, and the elastic requirements will have the boundary in a certain anisotropic direction. So you see these beautiful domains of lithium-rich domains and lithium-poor domains. So this is exactly what you would expect from thermodynamics. You have classical phase separation. If you do this experiment in situ, so now we're watching the phase separation, you see exactly the same thing. You see a phase boundary moving, and in a sort of a shrinking core effect, you see the phase propagating, changing from red to green, from lithium poor to lithium rich. And if you carefully analyze the composition of the material, you will see that thermodynamics is obeyed. You see either red or lithium rich, or you see green or lithium poor. There's nothing in between. So the miscibility gap is never occupied, which is what you expect from thermodynamics. This is what happens when you cycle the battery at a rate of about 6 hours. But what happens when you do this experiment much faster? So now let's go to a 30-minute cycle. So now we are proceeding at 10 times the speed. And let me run the movie for you. So this is the same experiment we're doing in situ. Rather than doing it over 6 hours, we're doing it over half an hour. And now you can see, as we intercalate lithium, you no longer see the moving phase boundary. In fact, you see the particle transition from green to red in a very continuous fashion. So what this means is that we are accessing the thermodynamically unstable compositions. So rather than having a phase transformation by forming a phase boundary, you have some sort of a metastable solid solution, which means that phase separation is not happening. So what's going on here? This connects back to the concept I was mentioning, which is the autocatalytic effect. It turns out that the resistance of inserting lithium into this material highly depends on how much lithium is in the system. This is a measurement that we did using X-ray microscopy, where we measure the interfacial resistance, so how much driving force is needed to put lithium into the particle. And this resistance is actually highly non-monotonic. It has the lowest value at about quarter filling, which means when you have about quarter of the lithium sites occupied, it's easiest to put lithium into the system. So what is the implication on the equilibrium property of the material? Well, the black line here is the open circuit potential if the system doesn't phase separate. So you have a non-monotonic chemical potential. This is classical textbook. This is what will lead to a phase separation. But when you start imposing a current on the system, you have to add the IR drop into the system. So you take the current, you multiply by the resistance I showed on the previous slide, and you crank up the current. Because the resistance is not monotonic, that means certain part of the system will have a lower overpotential than the other. So what I'm showing you in yellow here is the composition-dependent overpotential. This basically tells you it takes very little overpotential to insert lithium at quarter filling, and it takes a lot of overpotential to insert it at larger compositions. The consequence is striking. You can basically take the non-monotonic black curve, which is the open circuit voltage at equilibrium, and you will basically turn into a monotonic curve, which means it's continuously increasing. And again, textbooks tells us when you perform a stability analysis, when you have a current flowing, the system actually won't phase separate. So what I'm showing you here is that the autocatalytic effect, the fact that the kinetics strongly changes with the composition of an ion insertion material like a lithium iron phosphate, when you apply a current to the system, you can actually get the system to behave in a completely non-equilibrium manner. So this is the explanation behind why the system phase separates normally at a low rate, but it doesn't phase separate at a high rate, which again is something that is quite unusual and is something that has been noted many times before, but it was not until recently we have a complete explanation for what is happening. I want to now briefly talk about what happens if you stop the intercalation. So the previous slide shows you what happens if you intercalate from lithium 0 to lithium 1. But what if you stop halfway? And the reason is simple. No battery operates at constant current. When you use your phone, your current is dependent on time. When you drive electric vehicles, you are braking, you are charging. So the current is never constant. So what if you take lithium iron phosphate in its metastable state, so say lithium 0.5 iron phosphate, which means you're in the miscibility gap. Now, when you have a high current, that means you don't phase separate. So I'm showing this on the left as yellow, okay? So you have no phase separation, and you stop the current. When you stop the current, the system will naturally want to phase separate. And it turns out there is a very interesting pathway for phase separation, which is to park all the lithium in half of the particles while keeping the other half free of lithium. The benefit of this is you don't form a phase boundary. So this basically tells you that the phase boundaries are pushed out by parking lithium in half of the particles. So schematically on the right, I'm illustrating lithium poor particles and lithium rich particles. So ideally, this is what will happen because you avoid the cost of the interfacial penalty of forming the boundary. But it turns out that when we do the experiment, we don't see this stable configuration until a very long time, several hundred hours. And at any reasonable time frame, you actually see the intermediate behavior, which is forming the phase boundaries. So this is very strange to us because the classical picture of phase separation for a one-dimensional material like lithium iron phosphate is in order to form the phase boundary, you have to move lithium across the particle. But lithium doesn't move in that direction. Lithium only moves up and down due to the anisotropic transport of lithium iron phosphate. So the lithium would have to come out of one channel and go into another channel. But if it has a pathway to do that, it will rather just partition the lithium into separate particles. So it turns out that lithium can move efficiently in this material on the surface. So within the bulk of the material, lithium has no way to travel left and right in my schematic. Lithium can only travel up and left and right if it comes out of the particle and then enters in another location. This is the standard bulk behavior of the system. But it turns out in this material, there is a surface diffusion path where lithium can move very efficiently at the interface of the electrolyte and the lithium iron phosphate at a rate that is much faster than in the bulk of the material. And this is actually due to an assistance between the solvent molecules like ethylene carbonate, which basically allows the lithium to hop between one-dimensional conduction channel. So essentially what is happening here is you are taking a material which is insulating in plane in the bulk, but is highly conductive on the surface. And that allows lithium to basically phase separate within one particle. So let me take all of these rules and put it into a phase diagram. So for battery engineers, we're constantly thinking about, well, how do I engineer the material to be uniform and homogeneous? After all, this is what can give rise to excellent reversibility and lifetime. It turns out that you want actually a fairly resistive battery, because when you have a resistive battery, you can use that interfacial resistance to suppress phase separation. And it also turns out you need to have a very low surface diffusion coefficient so you don't allow the material to phase separate within the particle. So by embracing these design concepts, we can now pick our optimal design space. And it's very counterintuitive. It tells you that in order to have uniformity, you need to have slow kinetics and you need to have slow surface diffusion coefficient. And this is something that has not been realized for this material, but this is the design space which can give you very uniform intercalation. If you go to the diagonal on the bottom, where you have very low resistance and very high surface diffusion, then you have the situation that the material is extremely heterogeneous, both within individual particles and in the population. So now I've talked quite a bit about lithium iron phosphate. Let me now go to the opposite system, which is the layer oxides. So the layer oxides, unlike lithium iron phosphate, does not undergo phase separation in the standard compositions of interest. So it doesn't have the double well. So you might ask, well, why are we talking about phase separations and all of these effects when the system has a very boring phase diagram? Well, it turns out when you apply a current, the system begins to deviate from the expected behavior. So let me take another very common material, lithium, nickel, manganese, cobalt oxide. So this is what is used in electric vehicles. If you take this material and you cycle it, you put lithium in, you take lithium out, and you use X-ray diffraction to monitor the phase behavior. Because it's a solid solution material, from Vegard's law, we know that the lattice constant should shift continuously with the amount of lithium that you take out and the amount of lithium you put in. And this is exactly what you see when we do the experiment over 15 hours. We have continuous variations of lattice constant. And moreover, it's identical between taking lithium out and putting lithium in. So this is telling a very standard solute solution picture. But when you crank up the current, you actually get a very different behavior. So when you crank the current, so now rather than doing over, say, 10 hours, you do in 15 minutes, you actually see signatures of phase separation. Again, this is very strange because this material does not phase separate. There is no two-phase regime, no miscibility gap in this composition range. But if you look at the X-ray diffraction, you see a bifurcation. You see two lattice constants present at the same time, which is a tall tale sign of phase separation. But very interestingly, it only happens when you remove lithium, but it doesn't happen when you insert lithium, which is on the bottom of the plot. So this is something that's very interesting. It tells us that we have phase separations during dilithiation and only at high rates. So when we first saw this phenomenon, we thought, oh, this must be just a diffusion front, because the diffusion front can perfectly explain the observation. You have basically what I'm showing animation here. You have very slow diffusion in the particle, so you form a moving front, and when you do X-ray diffraction, the two compositional ranges of what it looks like phase separation is nothing more than diffusion. So indeed, the X-ray diffraction results can be explained by slow diffusion. However, if we took this picture, okay, and we took images of all these particles, we would expect a very standard behavior of a single peak histogram. So now, let me show you the picture. So we took these particles, we allowed the lithium to move freely within the particles, but not between the particles. And then let me show you what happens. So when you remove lithium, very slowly, you see this standard single peak distribution. So there are heterogeneity between the particles due to size effect, for example, and other variations, but it's a single peak. But if you do it very quickly, this is what we saw phase separation, you actually see a very different behavior. So rather than having a single peak in the histogram, so that means very uniform composition with some broadening, you actually see a bimodal distribution, which means that you have now lithium rich and lithium poor particle, and graphically you can see this. So this tells us that diffusion isn't the explanation, because if diffusion was the explanation, then you would see uniform and single modal distribution for both cases. So what is happening here? This is another really good example of the autocatalytic effect. So let me explain this briefly and we'll wrap up in just a minute. So we have heterogeneity in the system to begin with. So every particle is a little bit differently. So when we start to remove lithium, so now the reaction is getting faster and faster and faster. So that means the particle that has slightly less lithium to begin with will accelerate more quickly. And that's what I'm showing here on the top row here. This is where you are getting faster kinetics with the reaction extent. This is autocatalysis. But now if you do everything in reverse, okay, now you are putting lithium back in, the kinetics actually slows down. So any heterogeneity you have initially actually gets diminished. So this is the autoinhibitory effect. So by having this autocatalysis effect, you're blowing up, you're increasing the heterogeneity, and it only happens in one direction. And it's the direction in which the reaction kinetics is getting faster with the extended reaction. So I'll show you a schematic and I'll finish up here. So this is a movie of the same phenomena, but now you don't see the diffusion front anymore. You see the effect where select particles are receiving lithium preferentially as you remove lithium, but then when you put lithium back in, it's very uniform. So this is yet another example of autocatalysis. And then when you do this at the porous electrode level, so you have a very thick battery, you can still see the same effect. You have the moving front at the electrode level, but you still have this mosaic effect, this heterogeneous effect. So it is not just some random heterogeneity, it is a direct result of autocatalysis. So let me finish up here by showing the phase diagram. We now can construct a phase diagram to tell you where this would happen. It only happens when the reaction is getting faster with the extended reaction, but it doesn't happen in reverse. So for this particular battery material, it only happens on charging, but it doesn't happen on discharging. And the effect increases with the reaction rate. And this has nothing to do with diffusion. So to wrap up here, I've covered three themes: population dynamics, autocatalysis, and non-equilibrium thermodynamics. I have taken what appears to be strange heterogeneity, but then we try to understand them at the mesoscale in informing the design rules. We have three emergent phenomena: the so-called mosaic effect of interparticle phase separation, or the population dynamics effect. I talked about metastable solid solutions, so going against thermodynamics when you have a current. And I also talked about the so-called fictitious phase separation, where autocatalysis amplifies heterogeneity in the system. And from this, we can derive a set of robust kinetics mesoscale phase diagram. And with that, I'd like to thank all the people involved. I always joke that I have a Korean mafia in my group. Jung-Woo Lim, who did many of the work here on lithium phosphate, is now a professor at Seoul National University in chemistry. Jin-Hoon Hong is now a staff member in KAIST. And Ian Lee, who did the work, is now at the University of Michigan. Thank you very much.
Thank you for the great talk. And then please let me read a question for you. So here's the first question. Thank you for your talk. How much does the size and shape of each grain of the active material matter for the active population effect? Is this something that can be controlled?
Yeah, so basically the question pertains to the initial heterogeneity. So not all the particles are the same. So if the differences between the particles are very small, then you will have a very tight active population. But if you have a very wide distribution, then that would broaden the effect. So it basically tells you how much you will smear out the effect by having initial heterogeneities.
Yeah, thanks for the answer. So here's the second question. Great and impressive talk. I'd like to ask what the reason of the autocatalysis is. Can you explain why the lithium insertion rate varies with lithium composition?
Hi, Wucha. It's good to hear your question. So this is a great question. So why does the reaction kinetic depend on composition? This is really just a very simple consequence of point defects. So in order to insert lithium, you have to have lithium sites on the surface. So typically, the more lithium sites you have, the faster the kinetic. So this is really just a direct reflection of the active sites. And when we change the composition of the material in the battery, we're changing the active site on the surface, and therefore the kinetics change. So this is a very straightforward effect of composition on the kinetics of intercalation.
Yeah, thank you for the answer. So thank you again for your great talk. And I think due to the time constraint, I think we have to move on to the next speaker. So thank you, Professor William Chueh.
Thank you very much.